This video is a demonstration on how to do some common mineral property tests to identify minerals. Minerals are naturally occurring inorganic solids with a definite chemical composition and crystalline structure. There are thousands of minerals in Earth's crust, but we can identify them with some physical and chemical property tests. So when you're trying to describe or identify minerals, one of the first things we might think about is the color of the mineral. So color for some minerals can be useful, but both of these minerals are samples of quartz. Quartz comes in many different colors: clear or white, pink, purple, gray, yellow, lots of different colors. So color can be not a very descriptive property test. The other thing to think about is there are many minerals that are the same color. So these are all different minerals but have the same color. These are all similar colors but different minerals. So color, like I said, can be diagnostic for some minerals, but for other minerals it's not. One example of a mineral that we'll be looking at several times for this course is mineral olivine, and it is almost always a kind of olive green color. Here's a sample of olivine in a cluster, and here is a sample of olivine as a crystal, and you can see that it's got this pretty distinct green color, which doesn't vary often. The reason that one mineral can exist in multiple colors is because of chemical impurities in the mineral crystalline structure. So another property test that we can do that can be more diagnostic is the streak test. So for example, this is a mineral in hand sample that is kind of an off-white color. The streak test is the color of the mineral in powdered form. So to powder the mineral, we just rub it across an unglazed porcelain plate, and in this example we can see that the streak is white, which is the same as the mineral. But there are some minerals that have a streak that is a different color. This is a mineral called hematite, and it comes in a variety of colors. Sometimes it's kind of a metallic silver color, sometimes it's a rusty red color, and sometimes it's a very kind of shiny, reflective silver color, and sometimes it's more black and metallic looking. But every time we streak hematite, the color on the streak plate is a kind of a rusty brown or rusty red color. So in that way, streak can be a more diagnostic color test than the actual color in hand sample. Luster is a mineral physical property that describes the way the surface of the mineral interacts with light, or the way that it reflects light from its surface. There are two main categories of luster. One is metallic. So metallic luster is very reflective. The best way to describe metallic luster is that the mineral looks like a metal. So the color can be silver or gold or some sort of a platinum color, but color is not part of the luster description. It's just the way that the mineral reflects light. This is a mineral galena, and it has a metallic luster. If it doesn't look like a metal, then we say that the mineral has non-metallic luster. If it has non-metallic luster, then we'll want to describe it a little bit more. So for example, these two minerals both have non-metallic luster, but this one reflects light very well, like glass, so we say this glassy luster, whereas this one, it's somewhat reflective, but it looks more pearly, so we say that this is a pearly luster. Whereas another mineral that does not reflect light very well might have something like an earthy luster. There's also non-metallic luster descriptions such as resinous or earthy. Another property test that's really useful in identifying mineral is a property test that describes the way that a mineral breaks. So this is a quartz crystal. It has this shape because of its crystalline structure. But most of the time we don't see quartz like this because it doesn't have enough space it's growing up against other minerals, and so the crystalline shape is not evident on the outside. The other reason we don't commonly see this crystalline shape is that by the time we see the mineral, it's probably been broken. Quartz, when it breaks, it looks more like this. It breaks in a random pattern. This is another example of the random breakage of quartz. There are some minerals, however, that break in a very repetitive pattern. They always break the same way, and they produce flat surfaces that we call cleavage planes. The reason some minerals break in this way is because there are weak directions of atomic bonding in the crystalline structure. So this is a mineral calcite, and when calcite breaks, it breaks producing these very flat surfaces that we call cleavage planes, and you can see that there's 3 different directions of cleavage. So this surface and this surface are parallel to each other, so that's one direction of cleavage. This surface and this surface are also parallel to each other, so that is a second direction of cleavage, and then there's also a third direction. The other thing that we look for when describing cleavage, if a mineral does exhibit cleavage, we look at the angle between the 2 cleavage faces. In this case, it is not 90 degrees. It's at a different angle. When we look at a mineral like halite, we can see that it also exhibits 3 directions of cleavage. It breaks in 3 different directions of parallel faces, but the angle between the faces is 90 degrees. So when a mineral has cleavage, we will see repeating flat faces, and we will describe the cleavage by determining the number of cleavage planes and the angle between the cleavage planes. If a mineral does not cleave, we say that it has fracture. It breaks randomly. Some minerals have a diagnostic fracture. In other words, they fracture in a certain way, and quartz is one of those minerals. Quartz is a very common mineral, and when it breaks, it fractures, but it tends to fracture along somewhat curved surfaces and producing sharp edges between the fracture surfaces. Here is another example of a mineral that has really strong cleavage. This is a mineral called biotite. And you can see that biotite produces very flat sheets of minerals, and they break really easily, but they break in one direction, like sheets of paper, like peeling sheets of paper off of a pad. So this means that biotite has strong cleavage, but the cleavage is only in one direction. It breaks in one direction. Another example of cleavage is the mineral fluorite. And fluorite has a really distinctive cleavage of 4 different directions. 1, 2, 3, 4. And so, of course, the angle between the faces is not 90 degrees. So 4 directions of cleavage. And the last test that's very diagnostic for most minerals is the hardness test. So hardness is a mineral's resistance to being scratched. And we can quantify a mineral's hardness using the Mohs hardness scale. And it's a scale that goes from 1 to 10. So in order to test the hardness of a mineral, we compare it to other objects with known hardness. For example, a fingernail has a hardness of about 2.5. A copper penny has a hardness of about 3.5. And a glass plate has a hardness of about 5.5. There are other objects that can be used, for example, a steel nail, but since it's made from different alloys, it can have a hardness of 5 or 6, so there's a little bit of a variation. You can also use the streak plate as a hardness tool. This unglazed porcelain has a hardness of approximately 7. The mineral with the hardest mineral that is known is diamond with a hardness of 10. So that's the only object with a hardness of 10. So how do we test for hardness? So if we have a mineral and we want to figure out how hard it is, you can use an object with known hardness, for example, this penny with a hardness of 3.5. And we can try to scratch the mineral. So what I'm going to try to do is take an edge of the penny and produce a single scratch on the surface of the mineral. So I'm going to press it against the mineral and rub it along the surface, and I cannot see or feel any scratch produced by the penny. That means that all we know so far is that this mineral is harder than a penny. In other words, the hardness of this mineral is greater than 3.5 on a scale of 1 to 10. So we probably want to be able to narrow that down more. So maybe we will take another hardness tool, like a glass plate with a hardness of 5.5, and we can either take the glass plate and try to scratch the mineral again, but it's probably a better idea to take the mineral and try to scratch the surface of the glass plate. So I'm going to take a corner of the quartz crystal and I'm going to rub it over the surface of the glass. Hopefully you can see that it's produced one very distinct scratch in the surface of the glass. So since the glass plate has a hardness of 5.5, we now know that this mineral is harder than 5.5. There are few minerals that are very soft. They're soft and they can be easily scratched with your fingernail. So if you find kind of a undisturbed surface of this mineral and I scratch it with my fingernail, I can see that there is a scratch left behind on the mineral. Two things to keep in mind when you're doing a hardness test for a mineral. When you try to produce a scratch and you see a white powder, it could be that the tool that you're using was pulverized onto the surface of the mineral and therefore the mineral is harder than the tool. Or it could be that the tool, in this case my fingernail, pulverized the mineral. To see which it is, I often like to feel what I think is a scratch to see if it actually is a scratch, and it is. So that means this mineral has a hardness that's less than 2.5. So most of the time when we do a hardness test in a classroom setting, we can never determine exactly how hard the mineral. We can just determine a range of hardness. For example, this mineral is harder than 5.5, and this mineral has a hardness that is less than 2.5. There are some other mineral property tests that can be extremely useful in identifying some minerals, but most minerals do not exhibit those properties. One of those tests is a property test called magnetism. So here are three minerals. They might look pretty similar, just looking at them physically, but we could use a magnet to see if the mineral exhibits strong magnetism. And one way we could do that is if we have our magnet hanging from a string and we bring it close to the mineral, we can see if it's attracted to the mineral. In this case, it is. Then here's another mineral. We'll try the same thing. In this case, it is strongly attracted to the mineral. Here's another mineral that looks similar. We bring the magnet close by and there is no reaction. So these two minerals are strongly magnetic. Therefore, they probably are the same mineral or a variation thereof. There's a mineral called magnetite that exhibits strong magnetism. There are lots and lots of black minerals. Magnetite is almost always black. So to distinguish magnetite from other black minerals, a very easy way to do that is with the magnetism. But again, most minerals do not exhibit magnetism, so it's not a very useful test for most minerals. Another test that can be extremely useful for a very small group of minerals is the effervescence test. So I'll go ahead and write that out. And basically what that means is that the mineral reacts very visibly by producing gas when in contact with a very weak acid. So I'm going to go ahead and put gloves on, although the acid that you're using for the labs is a really weak acid, and so it would be pretty difficult to harm yourself with it. However, just to be on the safe side, we're going to protect our hands. So this is a very weak version of hydrochloric acid. And we would only do this test if we suspect that the mineral is possibly a mineral that would react to the acid test. So I'm going to pull out a few mineral samples that look similar to each other. Let's try these three. And this effervescence test or acid test, all it requires is that you put a small drop of the acid on the surface of the mineral and then watch closely to see if you can see a strong reaction. So if I look here, I just see the acidic water running off the surface of the mineral. I'll try it on this one. Again, the mineral is just running over the surface of the mineral. The acid is running over the surface of the mineral. And let's try this one. And hopefully you can see here that there's a strong reaction. And what's happening is the mineral is partially being dissolved and carbon dioxide gas is being released. And as the gas moves up through the acidic water, it's producing bubbles and it's changing the chemistry of the water. So now this mineral is a calcium carbonate mineral, meaning that its chemical formula has calcium, carbon, and oxygen in it. And when it interacts with the weak acid, the calcium is released as ions into solution. Some of the carbon and oxygen produces carbon dioxide gas. And then also some more of the carbon and oxygen produces bicarbonate ions in the water, in the acidic water. So again, most minerals do not react visibly by effervescing in weak acid, but if we suspect that your mineral is calcite, or a mineral similar to calcite, then you can do the acid test and it's very diagnostic for that mineral. So those are some of the main property tests that we use to identify minerals in the lab setting, and that will help us to identify most of the labs for the purposes of this class.